Okay, good morning. My clock is showing it's 11:01, so we'll get started. Um, Welcome to our webinar on medium voltage cable failures. My name is Bill Higinbotham. I'm the president of EA Technology LLC here in the U.S., and I'm responsible for North and South America. With me on the call today is Jorge Rivera. He's our vice president of sales, and he has the added benefit of speaking Spanish. So, George, you want to introduce yourself?
Hi everyone, and for those that are Spanish speakers, hablo español y le podemos ayudar traduciendo la presentación fuera de línea si se comunican conmigo. All right, back to you.
All right,
I'll be
great.
monitoring the chats, so if you have any questions on the chat, please ask through the chat, and we'll try to get to them at the end.
Okay, yeah, a little bit of a few logistics here. Please mute your microphones, and we'll enter your questions into the chat box. We'll handle questions at the end of the presentation. And of course, Jorge and I are available for any questions anytime after that. We love to talk. We will be providing a video copy of this, a link to a video copy of this PowerPoint, or the whole webinar when we're done. And with that, I'll get started. Okay, first, just one slide on who is EA Technology. We're a UK-based company that is best categorized as a medium and low voltage reliability company. We provide a lot of information, a lot of work in the partial discharge area. We'll talk about more of that today, but we make instruments, we do monitoring services, we do field surveys, we do a lot of asset health services, forensic failure investigation. So if you have something fail and you need to look into that, and you'll see some of the results of that in today's PowerPoint. We do a lot of consulting in grid modernization, net zero, electric vehicle impact on the distribution grid, asset management consulting in terms of ISO 55000 and other things. And most recently, a lot of work in low voltage grid reliability with monitoring and reclosers and hardware. So that's my only salesy slide, I promise. Let's get on to some other things. So the first question is, what is partial discharge? Talk about that. A lot of people are not familiar with it. A lot of people think they're familiar with it, but have been told a variety of different stories over time. But let's get into it. So partial discharge, the Wikipedia definition is that it is a flashover of part of the insulation system. It is a flashover, but it's not a flashover of the entire insulation system. Otherwise, you'd have a catastrophic arc flash. This is due to the electric field being greater than the withstand capability of that part of the insulation. And so this slide demonstrates it really well. If I look at a conductor and a ground, this green thing in the middle is my insulator, and I have say a void in the middle of it. I can model this as a series and parallel capacitors. For this picture, I've got 3 series capacitors. Going to make my life easy. I'm going to call all these capacitors have the same value. And what happens as the sine wave of the AC waveform is going up and down and up and down, at some point, the voltage across C2 exceeds the capability. The electric field exceeds the capability of C2 to withstand. And so what happens is that goes from some voltage to a very low voltage. You know, let's say we had 3,000 volts and 1,000 volts on C2, it breaks down. It goes to 0 volts. So now I still have 3,000 volts between my conductor and ground. So the voltage at C1 and C3 have to change from 1,000 volts each to 1,500 volts. And the way we change the voltage across capacitors, we all know, is to flow current through it. So it is a high frequency unipolar spike. And that current spike creates a number of side effects that we'll talk about, but that's what partial discharge is. It's actually a current spike as a result of a flashover. And we got a little video here. Hopefully that'll play. So you can see these little flashovers. On the right side, it's a little more consistent. and then on the left side you see it arcing over. This is classic partial discharge. Don't anyone tell you it doesn't exist. That black tracking on the insulator is characteristic of what you'll find after a long period of partial discharge. We take partial discharge and we break it down into three basic classifications: corona, surface, and internal discharge. So corona discharge, and lots of people around the world use the term corona discharge and partial discharge interchangeably. Corona is actually a subset. It is one form of partial discharge. It is where the discharge, this current, is going directly from a conductor through a gaseous medium. 99.99% of the time, that's air. So when you discharge directly to the air, that's corona. This is characterized by a buzzing, humming noise you can hear, a lot of radio noise that's generated. In the right light, you can actually see blue sparks coming off the conductors, and it's a result of geometry, construction, humidity. It's not necessarily going to lead to catastrophic failure right away, but its big problem is that it tends to hide more destructive forms of partial discharge. The next form is, and by far most common, is surface discharge. Surface discharge is where this current is going across the surface of the insulator, and that tends to damage the insulator. It tends to create a lot of side effects. It leaves that black carbon tracking shown in the picture below there, and a variety of other effects that do things like cause the copper to turn green. You can see in this picture the copper's turned green. So this is a very common, it's the easiest to find, but it's also the fastest moving and most destructive. Internal discharge, on the other hand, is the slowest moving and hardest to find, but it can take years or decades to lead to failure. So this is where the discharge is actually through the insulator. It's a completely contained void inside an insulator, and that would eventually grow to the point where it would catastrophically fail. And you can see in that picture that channel that's eaten through that insulator. So that's an insulator that's been cut in half, and you can see that channel that's eaten through it. It's the hardest to find in that it doesn't generate certain side effects, and it is there's nothing to see. You can do an inspection, you can tear it apart, but until you actually cut down and find the void in the insulator, you're not going to see anything at all. So visual inspection is of no use for internal discharge. So we've got these three types. We're going to talk a little bit more about them. When you have partial discharge, you have a variety of things that happen. Some of them we don't care about. We're going to call them benign. Some of those are very dangerous, and some that are actually useful in finding PD. So going across the top, we've got the electromagnetic spectrum, which, light, heat, radio frequency interference, anything that's in that spectrum, it generates light. Well, light is visible, and if I had a dark room and I stuck my head inside the switchgear, I could use that to find PD, but that's not all that useful. Heat in the infrared spectrum, heat is good and bad. We can detect it, but it is very hot. And this is not a lot of energy in partial discharge, but there's a lot of localized heat. It's plasma. A spark is plasma, and that's going to melt a few molecules, destroy a few molecules of the insulation every time it fires. So that's happening every half cycle. You got this happening 60 times a second for days, weeks, months, years. That is what destroys the insulation. In continuing down the electromagnetic spectrum, we've got RFI, or radio frequency interference. This is really useful. If you've ever been in a car in a lightning storm with the radio on and you hear the sparking and that comes through the radio, that's kind of how we detect partial discharge. Sparks generate a lot of radio frequency interference. They create a lot of broadband, and we can use that to detect PD. In the acoustic range, which is sound waves, this is not an electromagnetic effect. This is acoustic. It's sound, travels through liquids, solids, through gas, through air. It creates a little bit of energy in the audio band, which is what we can hear, and a lot in the ultrasonic band. So that is sound waves, but they're above the range of human hearing, up in the 40 kilohertz range. And that is a great method for detecting. There are a number of chemical effects that happen with surface discharge and with corona, but it doesn't happen with internal discharge because it's contained, you're not exposed to air. So when you have this spark in air, you have a breakdown of the air molecules that are ionized. And what happens is it creates, from the air molecules, it splits out the oxygen and the nitrogen. The oxygen forms ozone, which you can smell. If you've ever gone into a high voltage substation and you smell ozone indoors, you probably have partial discharge. Nitrous oxide doesn't smell, but it's very corrosive. And by itself, it's not too bad, but when you add any humidity, the nitrous oxide becomes nitric acid, and nitric acid eats through all the insulation we use in the substation. So this is why surface discharge happens at a faster rate. You've got heat and nitrous oxide that are affecting the insulation. Internal discharge, you really only have the heat, so they move slower. It's all kind of logical. Now, the nice thing, the useful fact is the smell. You can smell ozone. It gives you an indication something might be going on. And then there's this current pulse, right? We said PD is a current pulse. That has a variety of electrical effects that we can pick up. One is transient earth voltage. One is CPD or cable PD. Is a current. If we can measure that current, if we can put a transformer in place to measure that current, we can use that to detect PD, even though we may not be able to see it, hear it through ultrasonic, smell it, or anything else. So there's a variety of effects that are good, bad, and benign. What causes PD? We're going to talk a lot about that on cables today. The number one cause is workmanship. If the assets, the accessories and the cables and switchgear and all that are designed correctly, and most of them are, installation errors are your number one cause of PD. Contamination is another thing. Salt, coal dust, fly ash, pollution from a refinery, pollution from a chemical process, anything that affects the insulation, the permittivity of the insulation, or allows moisture to collect. We clean insulators because they get dust on them. Well, dust isn't necessarily all that conductive, but once I start adding humidity to it, and then dust will trap and hold humidity, that gives us a point for discharge. The environment, like I say, humidity, however it exists, whether it's airborne humidity or it's collected in dust on the surface, can be a big contributor to surface discharge. Salt air is even worse. I don't know if I've got any island utilities or customers that live right by the ocean. Salt air is a big problem. It causes a lot of surface discharge because salt air humidity is conductive. Mechanical damage, well, we're in the U.S., people tend to shoot insulators for fun. But any kind of mechanical damage to overhead insulators or any kind of insulation, which is going to change the electric field distribution, can cause discharge. Age is not a big factor. You tend to think that partial discharge occurs already. Well, it occurs the whole time. It may not lead to failure until 30, 40 years down the road. But as things get old, oil migrates out of PILC cables, and over time, insulation can dry out. So age is a minor factor. And the last thing is design. The design of the components, whether they're designed so that they're hard to install and installation errors occur, or because they're just designed so that there are some high stress areas. It happens. We've seen it in switchgear, we've seen it in cable terminations, we've seen it in overhead insulators. Poor design does exist from time to time. It's unlikely, but it does happen. So we're going to talk today about cables, and a lot of people out there are very familiar. There's a lot of people on this call that are a lot smarter than I am, but the question comes up a lot: why do we use shielded cables? And shielded cables from 2,500 volts up to however high you want to go are very complex engineered assemblies that have a number of components, and components you wouldn't expect if you're not familiar with the state of the art. Like semiconducting layer, what's that for? So what we have is, in a cable, we have a conductor. That conductor is not smooth on the outside. Imagine a stranded conductor. It's got bumps and that from the individual conductors. And so we put a semicon layer on that smooths it out. Then we have our insulator. Then we have another semicon layer that's there just inside the shield to smooth out any irregularities in the shield, especially when you have a concentric neutral where you have wires that are spaced apart. We want to provide a perfectly even conductive layer on the outside. So by having an even layer on the inside and even layer on the outside, we have a nice consistent electric field between the conductor and the shield. if you look at that on this picture here, right, so we've got our semicon layers, and between the semicon layers, we have an electric field. And that electric field is nice, evenly spaced. And then the shield on the outside of that contains this electric field, and anything that is outside that does not affect the electric field. So in this picture, I've shown a support brace, called a insulating support brace even. It has no effect on the electric distribution in the insulation. And that's really good, so that we can engineer, when we're a cable manufacturer, I can design an electric field strength and an insulation to withstand that strength, and unless that changes, life is good, and I don't get any kind of discharge. If we didn't have a shield on our cable, we would have a situation like this, where this electric field, these equipotential lines which represent the electric field, are not constrained within the insulation. They go on forever, effectively, until they hit a conductor. In this picture here, I've got the support brace. This support brace has a different permittivity from the insulation. The air has a different permittivity from the insulation. So what happens when you have a different permittivity, you get a concentration of electric field, a variation in the electric field, instead of this nice even distribution that we have in the shielded cable. That concentration of field is where you run into a situation where, well, now the field's higher, and the insulation withstand of that insulator may not be able to withstand it. So because we don't have a shield, we have to worry about everything that's around that cable, not just conductors. We have to worry about insulators, we have to worry about the air, we have to worry about pollution and all that. So if we have shielded cables, we're good. Now, very often we'll use unshielded cables inside switchgear. It happens. Here's a picture from one of my customers. They used a jumper cable inside switchgear. Not surprising, I see it all the time. That jumper cable is rated at the operating voltage. But because it's resting on that non-conductive brace, right where that edge is, you get a sharp corner, you get a concentration field, and you can see from these pictures, they got burn marks. These cables are 4 months old, and they're showing burn marks already. This PD occurred immediately upon energization and was detected via ultrasonic monitoring. Would have led to failure in a short order. The customer looked at it and said, well, I've got an insulator, I've got insulated cable, insulator on insulator, I'm good. Because we haven't been taught as engineers, power engineers, to really get too excited about electric fields and field control and stress control. And that's what PD is all about. It's electric stress control. And in this case, this was poorly done. And someone who's into stress control would know that. Your average high voltage electrician, if they're not into the whole field control and stress control, would not know that. And that's what happened here. A lot of people looked at this and didn't know what was going on. When we talk about stress control, we talk about cables, we've got this wonderful engineered cable assembly that's shielded. It's got semicon layers, so I can go a kilometer, 2 kilometers, whatever, and I know the field inside that cable is perfectly even. And I know that that field is less than the withstand capability of the insulation. So I am good from end to end. Problem is, cable's not much good unless I can get the electricity through it. So I've got to terminate that cable in something where the conductor comes out of the insulation. And if I were to just cut that insulation back like I was dealing with a 600 volt cable, I would have this massive problem right where the insulation was cut. So what we have are these stress control products, terminations, stress cones, cold shrink terminations, hot shrink terminations. They get a variety of different terms, but the whole purpose of them is to take these electric field lines, which are very close together in the insulation because it's controlled, and spread them out as they go to the totally uncontrolled air around the cable. And so you'll see something that might be a geometric shape, or it might have different stress control properties within the tube itself. The tube may be just a rectangular tube, but it has varying different permittivities in that. And so what we're trying to do is we're trying to keep those lines, once they're out in the air, as far apart as we can, or far apart enough so that the air doesn't break down. And that's really important. And this is where most cable failures occur, in these terminations. Because if we have a defect in the actual termination, so let's say, as this picture shows, we've got a gap an air void in the insulation. They didn't do the termination right. They didn't follow it right. And that there has a different permittivity, so it allows the concentration of field. It also, air has much lower withstand capability than XLPE, so I've got a bigger electric field and poorer insulation. I'm going to have a flashover. So I'm going to start getting arcing inside that cable. I'm not going to see anything from the outside. I may or may not hear something depending on how close it is from the outside, but I'm going to get this discharge. And I'm going to get it from the day that that thing is energized till it finally fails. So this is how the stress control relates to the failures. So here's an example of something we got in our forensic lab, and this is a cable that was not caught ahead of time. It failed. And you can see the XLPE insulation to the right and the semicon layer to the left with a big notch in it. Whoever did this termination was not well trained or having a bad day or didn't understand why this was important. You should have had a nice smooth circumferential line of semicon layer. They didn't do that. They ended up with a sharp point, which is going to cause concentration stress. There was likely a gap because the parts that go over this are not designed to fill that sort of opening. And so you got discharge, and you can see the discharge tracked in both directions until eventually it made a nice conductive path from the shield to the conductor, and it failed catastrophically. This is typical. Happens every day somewhere in the world. A cable's failing. It's not the fault of anyone except those who are managing the installation. Oh, sorry. You know, someone doing a cable termination, it's hard. If you've ever done one, if you haven't, if you're in a position where you're managing people who are doing it, try and do one yourself. They're difficult. They're done under terrible conditions. They're under the rain and the snow and the boss looking over and the refinery shut down and I need to terminate this cable. It's hard to do. It's hard to do under the best conditions, and it's really hard to do under bad conditions. So it's not someone's fault. It's just a fact of life. So, and there's a variety of different things that people don't really get on stress control beyond cable terminations. You know, cables terminate in switchgear typically, or out in the switchyard. But in the switchgear, there's a lot going on. If you look at some of these pictures, here's things that people do every day, and they don't give it a thought. I mean, how many of us use tie wraps? I've got a car. I think it's held together with tie wraps, and it pulls tight, and it causes a concentration of field. The permittivity of a tie wrap is different than the permittivity of air, and it's different than the permittivity of plastic. And so these things that we take for granted, you know, can cause PD. You can see in the upper right, there's PD going right from the tie wrap to this bus bar. In the upper left, rather. In the lower left, you've got two phases of unshielded cable. They're too close to one another. You see that white powder? That is the insulation actually starting to break down. The center bottom is where you've got a trifurcated cable, and at that crotch, the shields were cut back too low, and they're too close together. So where we go from the nice shielded portion to the unshielded portion is where things have gotten too close together, and we've got a lot of discharge. We've got that white powder. I'm sure we've got tracking inside, and a variety of other problems. So these are the kind of things you see. So why should we actually go and test cables? Well, that's kind of an obvious question. You know, an unplanned cable failure is a big thing, and so you want to be able to maintain your maintenance schedules. You don't want to have to do unscheduled maintenance. You don't want to have failures that shut down part of power system, whether it's a refinery, a batch process, data center, whatever it is. You want to do that. We're also worried about safety, right? Something's blowing up. That's never good. And hopefully it's all contained within the switchgear or outside where it isn't going to hurt anybody. But you have a failure, it can lead to other things. You know, so operationally, we don't ever want these to fail. As an asset manager, we're worried about risk. We're worried about what is the impact on the business. When should I replace these things? You know, I don't want to spend any money I don't have to spend. I don't want to replace things too early. I don't want to replace things too late. So if I've got 100 cables in my system, I don't want to replace them all. Okay, they all turn 40 years old. I'm going to replace them all. Can't do that. So what am I going to do? I want to focus on the ones that are about to fail or might fail next year or 5 years from now, so I can plan and I can establish a capital budget and I can hire crews to do this, and I can work around the issues. So testing cables helps us from an asset management perspective where we're planning, or it also helps us from the operational issue that maybe I find a cable that's bad or potentially going to fail. I can't take it out of service. That's always difficult. I can't replace it right now. But what I can do is I can have termination kits. I can have trained joiners on call. I can have spare cable so that if in fact it does go, I'm ready for it. You know, that's a big thing. People say, well, why test my cables? Because I can't change them out anyway. No, but you can be ready, and you can be ready for the ones that potentially might go. And maybe you have a redundancy strategy. Or maybe you go to the asset manager and say, we need to schedule some replacements here. There's lots of reasons to know why your cables are showing issues. You know, and obviously if you're replacing a cable before it fails, that's going to be a lot easier. If you look at this picture, would you rather replace one of these terminations or this one, which was a few weeks later? So you want to get to these things and fix them when you can. And, you know, and the partial discharge, which we started out with, is a factor in some 85% of unexpected substation failures. We've seen that over the years. You know, partial discharge is starting to break down insulation. Breakdown of insulation is what caused substation failure. So the 85% just kind of makes sense. The question we get asked all the time is, okay, I've got partial discharge. How long do I have before this cable fails? And anybody that can predict that, they're a better man than I. It's impossible to predict. It varies every time. But what you want to do is have some idea. You know, there is a point at which the failure starts that's not detectable. Sometime later, that failure becomes detectable. And at some point after that, it's going to actually cause a catastrophic failure. Sometimes that's minutes. Sometimes that's months. Sometimes that's decades. You know, you need to understand the type of failure you're looking at, the type of discharge you're looking at. You need to have an idea of you know, how fast those typically progress. What's my environment? If I'm in a high salt humidity environment, it's going to happen a lot faster. And I need to be able to schedule my testing frequently enough so that I've got some time between the detection and the catastrophic failure. You know, if it's a low consequence asset where you've got lots of redundancy, every 2 years is kind of typical. And at the other end of the scale, I've got something major. I'm going to lose 100 megawatts of data center floor. If I don't do something, I'm recording high PD. I need to detect that. And maybe I need to put in full-time monitoring to make sure that I know what's going on with those cables. So it's a decision based on risk-reward type thing. So the next question is why do cables fail? And I touched on this briefly, and that a lot of it's workmanship, but I'll tell you why I believe that. We all have that gut feel, but we did some research. So in the beginning, I mentioned that the EA does forensic analysis on failures, and we took 100 cable failures. It was just a 4-year period in which we had done 100 analysis of cables, and a lot of them were not relevant to what we're talking about. So we looked at 73 different cable forensic analysis, and then we categorized them. How old were they when they failed? What type of insulation? What voltage were they at? What was the installation and location like? What failed? And then proximate cause and ultimate cause. And proximate cause is the exact last thing that caused the failure. The ultimate cause is why exactly did that happen? And, you know, I'll get more into that. We looked and we plotted these failures over time. And what we saw was a bit of a bathtub curve. Not surprising. Most everything fails in a bathtub curve. And so we had this bathtub curve which you could apply to the different failures, and then we broke it down into infant mortality, random failures, and end of life. There's nothing you can do about end of life. End of life is end of life, but if you know your cables are getting to end of life, then you can plan for it. So testing that and seeing something's going on, or doing a forensic investigation and finding out that your cable's got impurities in it, it's 40 years old, and it's got water trees, it's got electrical trees, then you know you need to do something. Random failures, you know, it's hard to predict what that is, but the infant mortality, things where I install this and 5 years later it fails. Infant mortality in cables tends to be about a 10-year period, as opposed to electronics where it's a 10-hour period. You know, so you've got this time, you really want to reduce those, and that's where you get down into the workmanship and the testing and commissioning. You do all that right, then your infant mortality is going to go down. So first thing we looked at was what type of insulation are these reports on? And, we got XLPE, we got PILT, and we got EPR. And what we found was the XLPE and the PILT cables, the failure rates were pretty much in line with the ratios of installed cable that we got from a report from NETRAC. And so it's safe to say that the failure rates of XLPE and PILC are similar in our study. EPR was very low. It was 1% of all the cables that we tested. I don't have any information to tell me what that means. I wish I could tell you it means that EPR is much more reliable than XLPE. I don't know what that means, and we're trying to figure that out, but we don't have a good answer on that. Sometimes studies are like that. But then we get into the interesting stuff. Where did they fail? And you can see here that we've got splices, terminations, connectors, and mid-cable. Okay, everything but the mid-cable is where a human touched that cable, played with that cable, modified that cable, worked with the stress control of that cable in the field. And so you can see that 75% of the failures are at the point where somebody worked with the cable out in the field. So that's our first clue, that something's going on, and it's usually related to a person working with the cable. Now, mid-cable failures, a lot of it was mechanical. It could be manufacturing related. Sometimes they were defective cables, but it's hard to say what those are from. Now, as we get into the proximate cause, the proximate cause is exactly what they saw, what failed. And it's all over the map here. You can see there's a lot that it's hard to tell what to do about all this stuff. But we want to get into what the ultimate cause is. And I've got a picture of the Titanic there, because the proximate cause of the Titanic sinking was the boat filled up with water. Well, okay, we use a technique called the 5 whys. Why did the boat sink? Well, it filled up with water. Well, why did it fill up with water? Well, there was a hole. Well, why was there a hole? Because it hit an iceberg. Well, why did it hit an iceberg? And it goes back to the ultimate cause was the White Star Line was trying to prove a point about how fast their boat was, and they weren't safety conscious. And that's something you can address. You can't address iceberg. Well, you can address iceberg. You can address the proximate causes, but it's better to get to the ultimate cause and fix that. So we took these proximate causes, and for every one of these, we looked at the 5 whys, and we came down to the ultimate causes. And 66% of the time, it was workmanship. There were some other things, defects, design. Sometimes they put the wrong application, they used the wrong device. But, external damage is not a big contributor. Age-related failure is not a big contributor. It comes down to workmanship. A couple quick examples. Here's one of the cables from the study. It's 11 kV. It lasted 1 hour. We look at the cable. Lots of problems. No putty in the shear bolts. Poorly cut tubes. Shear bolts. Only one of them touching. This thing would have failed for any one of these reasons, and it failed for a variety of them. So, workmanship right there. Here's a second one. This one lasted 18 months. Okay, it's still in our infant mortality. And what happened is the 33 kV cable, the shear bolt edge was not filed down, cut through the various insulation layers, caused a failure. But you can see the insulation trimming, where the semicon was removed, that was done poorly. This could have failed for a variety of reasons. So again, workmanship. Here's one lasted quite a bit, 28 years. So this would be in our random midlife failure. It failed in mid-cable. Why did it fail? It failed due to moisture. Moisture infiltration. We can see when we look at it on on an electron microscope, we see electrical trees, we see water trees. Water trees aren't so bad, but they tend to lead to electrical trees. This is good to know, because maybe I'm an asset owner and I've got 100 similar cables running in similar environments. I better plan on some more failures here. I'm not necessarily going to run out and replace them, but at least I know what this cause is. If I get any other mechanical damage, I could have a failure. So these sort of things lead to the numbers that I showed above. What can we do about it? Well, we've got new installations, And obviously, if your workmanship is the problem, the biggest problem, then you've got to make sure your joiners are well trained. You've got to have good instructions. You know, you can't rely on the 4-pager that came with the cable termination kit and say, here, do this. No, you need detailed procedures. You might want to talk to the manufacturer of either the cable or the accessories and say, you know, we're having these failures. What are we doing wrong? What can we do? Or you know, change your equipment selection. If you don't have a really good system in place for doing hot shrink terminations, well, maybe you switch to cold shrink instead of doing hot shrink wrong. You know, so there's you really want to give this some thought when you're doing new installations. Problem is, we've got a lot of existing equipment out there, and we've got limited things we can do. Partial discharge mapping of the cables, partial discharge testing of the cables is really good. You can replace cables ahead of time, maybe as a result of finding PD. You know, discussing with the manufacturer, I've got this, I'm getting these failures, what can I do about it? Visual inspection is pretty limited because you can't see most of the cables. So what are we going to do? So from this study, what did we learn? Cables do have a predictive reliability. 35% of all cables will fail in the first 10 years. Cable failures occur in the first 10 years. Sorry, said that wrong. And you know, it's in the terminations and it's workmanship. So we can fix a lot of the workmanship and we can do more training, but as someone once said, we can't fix stupid. This is actually from a cable termination where the joiner did not know what to do with the white mastic, so he made a smiley face. This cable failed pretty quickly. You know, we got to look at workmanship. So if we can't undo the past, we've got these cables that are out there, what can we do? Well, we can do partial discharge testing. It's a great way for testing a cable. You know, testing cables is challenging because most of the cable isn't accessible. They're buried. They're hidden underground. So what do we do? If we can get to the ends and test from the ends in, we can find partial discharge anywhere in the cable. So the mechanism for partial discharge testing in cable, or partial discharge current in cables, is somewhere along the line you're going to have a discharge current. That discharge current is going to try and find a path to ground, and that path to ground is through the shield. So if we have this current path going down the shield and we can put an HFCT or high frequency current transformer around that ground strap, then we can do a test, and we can test for parts of the cable that may not be accessible. You know, we can't go an infinite length, but we can go pretty far, and that length is going to be controlled by the noise floor and the level of discharge and all that. But it's certainly better than looking at a cable that disappears a hole in the floor and say, well, I don't know what's going on. So this high frequency current transformer, there's a variety of different things. They're also called RFCTs, or radio frequency current transformer. It mounts on the ground strap of the shielded cable. We don't want to mount on a conductor for safety reasons and also for saturation reasons. If I've got 500 amps going through a cable and I'm trying to pick up 500 microamps on a transformer going through the same bore of the transformer, that's kind of hard. There should be very little current flowing through the ground strap so I can be more sensitive. If it's a split core, I can clamp it around an existing cable. This picture down the lower left are actually environmentally hardened HFCTs that can go outside. If we have outdoor cables, we have outdoor grounds, we can do that. And we're also showing a hot stick where you can temporarily use the shotgun hot stick to mount an RFCT on a ground strap for spot testing. Here's some examples of HFCT installation, some permanent installation, some temporary testing installation, and my favorite from quite a few years back is the old put on the bomb suit, go right up to it and install it live. We don't do that a whole lot anymore. Permanent install of HFCTs is more common, but there's usually a way to get an HFCT on the ground strap. Does it work? Well, we all want to know, does it work? Well, there's a utility in the UK. They tested 191 cables. Nice thing is they tested them, but they didn't replace them. They didn't repair them. And what they found that 17% of their cables tested in the red, 14% in the green, in the yellow, and 160 of the cables, I'm sorry, not percentage, but cables, were in the green. And so what did they do? They left it. Within 2 years, 41% of the cables that were classified in the red failed. 27% of the cables that were in the yellow failed. Less than 2% of the cables that were in the green failed. So we can see that if I had just addressed the red cables, I'd be better off. If I addressed the red and the yellow cables, I would have had a much smaller cable failure rate over those 2 years. So yes, it is effective. This is real world data. A lot of people talk about online testing, offline testing. The obvious big problem with online testing is that you have to take an outage. Take this cable, disconnect it, take it out of service, bring in test equipment, and you've got kind of two choices for test equipment. One is the VLF, or very low frequency, 0.1 hertz or 0.01 hertz, and that's what that picture in the middle is some VLF test equipment. It's still pretty hefty. I need to re-energize this line to line voltage or higher. The picture on the lower right is a 60 hertz or a line frequency test where they're actually energizing it at 60 hertz, which is better than 0.1 hertz. It's going to have more of a realistic effect. But this was 3 tractor trailer loads of equipment just to energize these cables to 300 kV. So your test equipment gets very large for offline testing. So I got to take an outage. I've got to have very heavy test equipment and a lot of money and time involved. On the left is some stuff, and arguably it's stuff by EA, but it's handheld online test equipment. We're testing at 60 hertz, which is good. We are testing at line voltage under normal operating conditions. We're testing with current flowing because current will cause things to increase. If you have a crack, that crack might expand with temperature. So we're a big fan of online versus offline. You can do many more cables in a given period of time. You can do it with less expensive equipment. You can do it with less trained operators. There's a bunch of advantages. It's not as effective as offline testing. So maybe you've got 100 cables again, like my old example. I test 100 cables. I find out that 5 of them are showing something, and maybe I do an offline test of those 5, or maybe I just plan on one of those 5 failing. So it's a balance, but scanning a lot of cables with online test equipment can be very helpful. When we look at the data, there's a variety of information on the data that we use. This is a phase resolve plot, which shows us each dot is an event that occurs and where it occurs on the sine wave. The bottom is a waveform of the actual current pulse. This is the actual current being generated by the PD. And so we can see that we've got some stuff in the negative half cycle, we've got some stuff in the positive half cycle, the peaks, and my waveforms look like PD should look like. That's real PD. Random noise, on the other hand, there's lots of sources of random noise. We're looking for very low levels. We're looking for millivolts and microvolts, milliamps and microamps. If it's distributed across the sine wave as we've got here all the way around and the waveform looks like noise, it's probably noise. It's probably not related to PD. If it's synchronous with the power system, it'll end up in groupings. Here's a picture where it ends up in groupings, but it ends up in 6 groupings. And they're very narrow, which means my phase angle is not moving very much back and forth. And there's 6 of them. Well, that sounds an awful lot like an inverter or a VFD or something like that. And that's, it may be synchronous with the power system, but it doesn't look anything like our first picture. Very often, you'll get both in the same. Here I've got the vertical spikes of a VFD, but I've got those 2 clouds half a cycle apart, positive and negative, showing me that I've got, something else. So what I do is if I look at the peak levels, well, the peak levels are coming from that VFD. That will be very misleading. So what I'm going to do is I filter out those, and I end up with something like this, where I've got my 2 clouds, got my positive, I've got my negative, I've got each dot represents one event, got a lot of events. This is very clearly PD, and I can get a reasonable level of it. So all I've done is I've filtered at 500 kilohertz and taken everything below that. I've gotten rid of everything below that, and this is what I'm seeing. So in summary, we're going to look for our events. We're going to look at our waveforms, look for 2 clusters 180 degrees apart, and we're going to look for a spike that is indicative of PD. The levels are tough. With an offline test, you can have exact levels and you can see what the PD is in it. We look at levels and we're more worried about the pattern, and we're more worried about how clean the waveforms are. We're not going to get too excited about the levels. If they are very low, it's not a concern. If they're very high, it's a concern, but the borderline stuff just keep testing, seeing if it gets worse. Sometimes when you're doing testing, you can get a nice clean signal. This is from one of our customers in the UK. We see our first pulse, we see it reflect from the far end of the cable, we see the direct pulse reflection, beautiful picture. What we can do is we can use these as they reflect back and forth and the times that it takes, and we can actually calculate the distance from the HFCT to the fault. This doesn't happen all the time with online testing because we have noise floors, we have things connected so we don't get great reflections. Offline you can do this, but occasionally online we can do it. So probably about 20% of the time we can actually do an online test and determine the distance to PD. Questions come up a lot is how long cable can I test? Well, how clean is your cable? How much noise is there? And how big is your PD source? Those two are going to affect it. So we can't, definitively say that you can test a 5-kilometer cable and not a 6-kilometer cable. But if you're testing a 5-kilometer cable, you might not be able to detect as low a PD level as you could on a 4-kilometer cable, that sort of thing. Tape shielded cables, where they're in a wet environment and they have lots of corrosion, are going to get high inductive and you're not going to be able to test them much at all. But if you've got good clean shields, you should be able to go, a few kilometers reliably. If you've got access to both ends, you can test the same cable from both ends. That's a really helpful thing to do. You can also, in your terminations, you're going to want to test for TEV and ultrasonic, which is other parts of that our instruments do. These are cable failures. The discharge in the air is creating a lot of ultrasonic energy. So if you're doing a cable test, also do a TEV test and an ultrasonic. That's going to give you a really good indication of the health of your cable. Really quickly, EA products here as we wrap up. So EA's got a product called the Cable Data Collector. It's designed for an untrained crew, so a crew that is not PD experts, they aren't doing the analysis themselves. They need to be able to use a laptop, and they need to be able to hook up the HFCTs to the ground strap. So they need to be high voltage qualified, but they don't need to be PD experts. They put this on, runs for 10 minutes, it collects a lot of data. The data comes back to EA, where we have experts in the US, Australia, and the UK that can do this analysis and give you a report cable by cable. So you can send out a crew that's not a bunch of experts. They can run through and do 50 cables in a day. A couple weeks later, you get a report, and you've got a good thing. You can also use our UltraTev Plus 2, which supports one HFCT, and you can do a test and you get results right there. It takes a few minutes to run a test. With the right training, you can do the interpretation. You can also save the data, send it to someone else to do the interpretation, whether it's us or an expert in your organization. That's a great tool. It also includes the TEV and ultrasonic, so you can do all those testing at once. It's also got an environmental sensor, so you can record the humidity when you're doing these tests. So those are two of your options. So there are other manufacturers out there that make products that'll do this as well. So last slide, the number one cause of failure, some of the things we learned here today is the number one cause is workmanship. We know that very often impending cable failures can be found by PD testing. There's a variety of tests you can do non-intrusively without taking a cable out of service. Instruments are great for the asset management aspect of it. And you need to look at criticality and risk. If I've got a cable that's feeding a little podunk situation down the road, that's a little different than if it's feeding Wall Street, it's feeding a data center floor. So you need to weigh risk into it. And last but not least is condition monitoring. Full-time monitoring is going to give you the most information. So it costs you the most, but it's going to give you the most information, and you can see things evolve and you can find out much quicker. So with that note, I'll leave it up to questions. Hopefully this has been helpful. And George, if you've got any questions for me that have been posted, please let me know.
Yeah, we have quite a few questions. I'll start with if you could talk further about the effect of temperature and humidity. You mentioned just a moment ago that the temp and humidity sensor, why is that important?
Okay, well, I mean, when we talk about this electric field, the electric field is something we want to control, and anytime we have anything conductive in that field, it's going to affect it. So humidity is a little bit conductive. Salt humidity is very conductive. So if you are near a body of salt water, that's going to, your cables and your terminations and anything exposed to air is going to degrade much faster. Temperature, in and of itself, temperature tends not to play a big role. Obviously, temperature interacts with humidity, but we're worried about the relative humidity. And the temperature of the conductors, we have seen a situation not that long ago where they got PD at the same time every afternoon, and it turned out that they had a higher load in the afternoon, and that was causing a crack in the termination to expand and cause the PD. And when there was no load on the cable, there was no PD. So yeah, temperature does play a small part.
Okay. How does the electrical or water tree phenomena relate to PD?
Sure. So water trees are where you might have a cable immersed in water, and the electric field will draw the water in. Electrical trees or water trees are not detectable via PD. They do not cause any PD. They cannot be tested for with PD. However, over time, electrical trees or water trees can dry out, and now I have a void where that water was, and that void is going to become an electrical tree, and that will generate a fair amount of PD, which can be seen either in a PD test or when you do a forensic investigation. I showed you those microscopic pictures of the electrical trees. They will lead to failure because the PD will advance until the insulation is eaten away and it flashes over.
This question came up when you had the diagrams up of the components of a cable. Is the semicon the layer that contains the electric field in the of the cable?
Okay. No. The electric field is contained by the shield, but the shield is made up of discrete wires or discrete tapes. The semicon layer kind of allows that to become a nice, smooth electrical surface, if you will. So I guess the answer is together, the shield and the semicon layer form the barrier for the electric field.
Okay, and the example where you had the unshielded cable that was resting on that non-insulating bar, what did they ultimately do there? Do you know?
Okay, so they made a variety of geometric changes. So, spacing stuff out is always good. So what they did is instead of the cables resting on the corner of the bar, they turned the bar so the cables were laying flat on it. So that reduced the geometric sharp point. They also added quite a bit of insulation sleeving and that to the cables so that they were further away from that conductor. And that's what ultimately solved it.
Okay. Just more of a comment than a question. Maybe worth mentioning that non-contact volt detectors do not work on the shielded part of the cable. With the cable live, and the non-contact detector will show dead if it approaches the shield part of the cable. It might be worth mentioning that if one touches a live termination, you might get shocked or worse.
Yes, that's right. So if you have an unshielded cable and you bring a non-contact voltage sensor up to it, that electric field, right? Remember that picture, electric field extends out past the insulation. So the non-contact sensor, which is a field sensor, picks up that field. If I put a shield around that cable, I now have that electric field contained within the shield. And so if I go to that shield or outside that shield with a non-contact sensor, I'm not going to see anything. And so the shield is ground and the shield is safe to touch and the sheath is safe to touch. But obviously if you start digging into there or go to one of the ends, it's still live.
Yeah. Does the bend radius, if bend radius violations can cause mid-cable issues and also the pull tension? Just more of a comment than a question there.
Oh, that's absolutely right. I didn't mention that, but if you have, remember, we've got this engineered system. We've got insulation of a certain width, and it's all designed to attain the shield. If I do anything to affect the integrity of that insulation, so if I have a bend radius violation, that insulation at the bend is going to be compressed. On the outside, it's going to be stretched, and on the inside, it's going to be pressed. It's going to change the size of that. And now I've got an electric field distribution that is different. Well, the field is different, and the insulation may be smaller, or maybe kinked, or may generate a gap. Yeah, so anything that mechanically affects the insulation can cause PD. And by the way, I wanted to say that, you know, our time may be running thin, but I will answer questions as long as people want. That we don't have a hard stop at 12 o'clock. So.
Okay. Yeah, we have, maybe a few more, half a dozen. Okay. So, can a cable with a severely deteriorated shield or the concentric wires be effectively monitored with PD testing?
That's a tough question. If you've got a shield, concentric wires that are broken, and you don't have, well, certainly if they're completely broken, it can't be tested. If some of them are broken in different spots, it's going to limit the effectiveness of the testing. I would be concerned about relying on the test results from any cable where I knew the shield was compromised.
Yeah. Can you define what is XLPE cable?
Sorry. Sure. That's most cable today. The biggest percentage is XLPE, which is extruded cross-linked polyethylene. It's used for everything, even for, and whether it's home wiring or 500 kV wiring, most of it is XLPE. The other insulation is PILC, or paper insulated lead covered, and that's where oil impregnated paper was wrapped around the conductor as an insulator.
Okay. I think we kind of covered this. It may have been before you went into it in the slides. Maybe worth mentioning again. If offline tests involve re-energizing back to line voltage, does it offer any benefit over an online test?
Okay, well, yeah, offline tests are beneficial for a variety of reasons, that you can vary the voltage level up and down. You can do it above line voltage, you can do it below line voltage, you can find out where the PD starts, where the PD stops. You do have to be careful when you re-energize the cable. If you ever use XLPE and DC high pod or DC testing, you can end up with cable failures, but that typically doesn't happen with modern VLF equipment. Yeah, offline is a great test. It's just a very expensive, very time-consuming test, and there is some question over whether a 0.1 hertz or 0.01 hertz is representative of a 60 hertz situation. So that's where I strongly recommend test all your cables online at 60 hertz, and then do offline testing for the very small percentage that you actually detect PD on.
Is it better to take online testing, cable testing during high load conditions, peak hours?
It doesn't play a big part, because partial discharge is a voltage phenomenon, not a current phenomenon. So when you have higher system voltages, you're more likely to have PD. But if your system voltage isn't varying much, it doesn't make much difference, with the exception of the high load causing thermal expansion and potentially causing cracks to be more visible. But that's not that common. So I would not say that you really ought to test at high load.
Okay. These are very random, not in any order.
That's fine.
Regarding age, you gave the list of the different failure modes from those forensic investigations that we have. Regarding age, even though it's a small factor, is there any general rule or guideline on when cables need to be replaced based on age?
Well, we saw from that survey, and I should point out that we're in the process of updating that study. We've got another 200 failures we need to look at, but it's taking time to go through them. But from that study, we did see an uptick, the end of the bathtub curve, in the area of 40 plus years. So I'm sure the manufacturers have a recommendation of what the cable life is, but it tends to be in the 40 to 50 years for XLPE is where you start seeing a wear out mechanism.
Are HFCT, RFCT susceptible to magnetic field or other emissions?
Because it's a toroid, unless you have a magnetic field, an alternating magnetic field of a sufficiently high frequency going through the middle of the toroid, it won't play much of an effect. Our HFCT is shielded on the outside, and because the toroid is really looking for current flowing through that hole in the middle. So you're not going to get a lot of that unless you're right on top of some very high frequency magnetic field generation equipment, like a motor or something like that, and you're right on top of it.
Is permanent monitoring available through the cloud?
Well, I mean, you need the hardware to be installed on site, but the way our monitor works is you connect it up to the cloud, and then remotely someone does the analysis. All monitoring, all good high quality monitoring requires a human to look at it and say, okay, this is noise, this is PD, and that's all done through the cloud.
Okay, but you can still have alarm points.
That's right. You can have alarm points for either hardware failure or as a point of this is when I need to look at it. And you can do the analysis locally, or you can have someone do it remotely. So there's a variety of different options you can go through.
Any ideas why cables in wind farms fail so much?
Well, hopefully there's nobody from a wind farm listening, but I'm going to say low bidder. The wind farms are built at a very low profit margin, and so they tend to use low bidder, least expensive cables, maybe not as qualified technicians. You know, if you think about a electric utility putting in a cable, they're going to own that cable for life. They're going to own that cable for 50 years. If it fails in 50 years, that's a problem for them. Wind farms are built by someone who's going to turn them over and sell them to somebody else. I think that's the number one cause. You also have some effects from inverters and that might cause voltage spikes on it, but I'm no expert on that, I have to admit.
Can multiple cables be tested at one time?
Well, I mean, if you use full-time monitoring, you can test. Yeah, you can hook up with our system. You can hook up, I'm going to say, 40 three-phase cables all at the same time, and test all of them. If you're using one of the handhelds, we either support 3 HFCTs, which allow you to do 3 phases at one time, or with the +2, you could do one at a time.
Okay. Doesn't service-aged cable with copper ribbon shielding limit PD detection to very short distances? You want me to read that again?
No, I can get that. Yes. So if you have an aged cable, that goes back to where we're talking about a tape that is helically wound around a cable, and you have lots of contact area. Over time, if you get corrosion on that overlap, then it is going to limit the distance that the PD testing will be effective. I think I said that, but if you have corrosion in the overlap, you'll have a problem. And with very old cables, especially if they're direct buried or they're in high humidity areas of that, you can get corrosion on that tape.
Can you do PD testing at 180 hertz?
I can't. I'm sorry, I don't have any way. I'm not familiar with anybody doing 180 hertz.
Not even offline?
No, they're doing lower. They're doing VLF, low frequency.
Right. Oh, I guess this is going back to that earlier question about the severely damaged shield. NETA spec recommends a shield continuity test.
Yes, definitely do a
common.
shield continuity test if you have any concerns about the quality or condition of the shield.
Someone was asking if a certificate is available for attending the presentation. If you can send me an email to sales@eatechnologyusa.com. That's right here on the screen. Let me know who you are, and we'll get one to you. And a question about, is the webinar available offline? Yes, everyone that registered and or attended will be getting an email probably Thursday with a link to the recording. And let's see. Can PD inside a transformer be detected from the cables attached to it?
Yeah, sometimes you can detect it. Sometimes you can also detect it with TEV or ultrasonic. For a transformer, an oil-filled transformer, dissolved gas analysis is your best bet. It's much more sensitive than any electronic method. But yeah, putting the HFCT on the grounds of the cables or on the grounds of the transformer itself will detect it. But I don't think it'll detect it too far away. I don't think you can go to the far end of the cable.
It won't be in the coil then.
Sorry?
It won't be inside. It'll be more in the cable compartment.
Yeah, if you have a cable termination box, you know, very often you'll get, again, it's a termination, it's where workmanship's taking place. You'll get PD in there, and you can test that with TEV, ultrasonic, or HFCTs.
Unless there's any last-minute questions, that covers our, and we're just a few minutes over the time.
All right. Well, thanks everyone for attending. I appreciate it. As I said, if you have specific questions, you want to talk, I'm available. George is available, and you know, that's what we exist to help you out. So again, thanks for attending. Have a great rest of your week.